Good evening friends. Today we are discussing flow through pipes. We have loss of energy in the pipes classified as major losses and minor losses. When a fluid is flowing in a pipe, so there will be some loss in the energy possessed by the flowing fluid. So that loss of energy we are classifying under two headings. One is the major loss and the other one is minor loss. So the major loss is due to friction in the fluid flow. Why this friction happens? The fundamental property of the fluid, that is viscosity, leads to the major loss. And even if there is a friction between the fluid and the wall of the pipe, so that also result in major loss. So under major loss we have two equations, that is Darcy-Weisbach equation, the other one is Cheggy's equation. And why the minor loss occurs? So there will be loss of energy in the flowing fluid due to when there is sudden expansion of the pipe, that is the diameter of the pipe from D1 is suddenly expanded to diameter of the pipe D2, or when there is a sudden contraction in the pipe, that is all of a sudden there is a decrease in the diameter from D1 to a smaller diameter D2. That means from a bigger area the fluid is entering into smaller area in case of contraction. In case of expansion, from smaller area all of a sudden the fluid enters into bigger area. Then if there is a pipe bend, that is in the direction of the fluid flow in the pipe, if there is a sudden bend taken place in the pipe, so that also result in loss of the energy. Then external pipe fittings like collars and T, right? So when two larger pipes which are horizontal is connected with one vertical pipe, then we are taking the help of a T to join two horizontal pipes and one vertical pipe. So when there is external pipe fittings, then also there will be loss of energy. Then we have any obstruction in the path of the fluid flow, that is obstruction in the pipes, that also leads to loss of energy. So coming to major loss, that is due to friction. So we have the derivation of Darcy-Weisbach equation here. So what we are doing here is considering a uniform horizontal pipe, in the sense the diameter of the pipe is same throughout. So there is no change in the diameter, that is there is no expansion or contraction. So we are considering a horizontal pipe having the steady flow as shown in the figure. P1 is nothing but the intensity of pressure at the section 1,1 and V1. So that is velocity of flow at the section 1,1. Then L, that is the distance between the two sections 1 and 2. That means the length of the pipe considered between the sections 1 and 2. Then D, small d, that is the diameter of the pipe. Then we have F dash, that is the frictional resistance per unit area per unit velocity. Then HF, that is head loss due to friction. We are going to derive the expression for this head loss due to friction, that is HF. So P1 and V1 are the pressure intensity and velocity of flow at section 1. Similarly, P2 and V2 are the pressure intensity and velocity at section 2. Now applying Bernoulli's equation between the two sections 1 and 2, we have the sum of the three heads, that is the pressure head plus kinetic head plus the datum head at section 1 is equal to the sum of pressure head plus kinetic head plus datum head plus additionally we have head loss due to friction, because friction is nothing but the force against the flow. If you consider the section 2, so we have head loss due to friction. That means between the time the flow taking place from section 1 to section 2, there will be some loss of energy taking place from section 1 to section 2. So that is due to friction. So head loss is nothing but energy loss. So there will be energy loss taking place by the time the fluid reaches the section 2. So additionally we have this head loss due to friction. So that is HF. Since the pipe is horizontal, we have Z1 is equal to Z2, which gets cancels on both the sides of Bernoulli's equation. Then we have V1 is equal to V2. That means velocity of the flow at point 1 is the same as velocity of flow at the point 2, as the diameter of the pipe is same. So there will be no change in the velocity. It is the flow is steady flow. In the sense, there is no change in the velocity with respect to time. So the Bernoulli's equation what we have written earlier reduces to P1 by rho g is equal to P2 by rho g plus HF, because velocity get cancelled on both sides and Z values also cancels on both sides. Now HF I can write it as P1 by rho g minus P2 by rho g. Taking rho g as the common denominator, taking LCM, we have P1 minus P2 is equal to rho g into HF. Now F, capital F, that is the frictional force. So that is written as frictional resistance per unit area per unit velocity into velocity to the power of n. So this is the Darcy-Weisbach frictional factor. So it means to say that my frictional force is proportional to this frictional resistance and velocity to the power of n. The value of this small n varies from 1.5 to 2. So now the frictional force can be written as frictional resistance F dash into, we have written here unit area. So unit area of the pipe. So pi into d. So since the pipe is considered as a rectangle, though it is having the circular cross section or it may be having the rectangular cross section. So the area between the two sections 1 and 2 will be considered as the rectangular area. So here the depth is nothing but the diameter d and the length is taken as L. So the total wetted perimeter, in the sense I am considering the perimeter from the section 1 to section 2. So that is given by pi into d, and the length of the pipe between the two sections 1 and 2 is taken as L into velocity to the power of n. So that is the value of n. I am taking maximum of 2 here. So finally I can write that my frictional force is directly proportional to frictional resistance into velocity square. So F dash frictional resistance into, as I said earlier, so pi d is taken as the perimeter into length L into V square. Now the three forces acting on the fluid between the two sections 1 and 2 are nothing but frictional force F1 that is taking place against the flow, and the pressure force at the section 1 that is nothing but pressure P1 into area A, and pressure force at section 2 that is nothing but P2 into A. Now resolving all the forces in x direction, so we have P1A. Since it is acting from left to right, it is having plus sign. Then P2A. So this is the force acting opposite to the flow. So that is from right to left, it is having minus sign. So minus P2A, and then we have the frictional force that is also acting from right to left, so having minus sign. So minus F1. So the summation of all the three forces as taken as 0. Now taking A common, we have P1 minus P2A is equal to taking this F1 the other side. So F1. So my F1 is nothing but my frictional force. So that is the product of F dash into PL into V square. Now P1 minus P2 is equal to F dash into PL into V square by A. Now P1 minus P2 we have already shown it as rho into G into HF. So this P1 minus P2. So I am writing this rho G HF here. So is equal to F dash into PL into V square divided by A. So HF is equal to, okay, taking this rho G to the denominator. So I have F dash by rho G into P by A into L V square. But P by A, the ratio P by A, P is nothing but the perimeter, that is the product of pi into D, A cross sectional area pi D square by 4. So simplifying this, so it is 4 by D. So substituting this P by A as 4 by D, I have HF is equal to F dash by rho G into 4 by D into LV square. That is F dash by rho G into 4 FLV square by D. You can conclude that my HF is equal to 4 FLV square by rho GD. But if I go to the next step, so I am writing my F dash by rho G as F by 2, where F is called as coefficient of friction. So replacing this quantity F dash by rho G by F by 2, the equation is finally written as HF is equal to 4 FLV square by 2 GD. So that will be considered as Darcy-Weisbach equation. Thank you.